seminar. It's probably the last. I think it's probably the last one for a while. So let me remind people online that we are recording this. So if you don't want to appear in the video, this is a good time to shut off your camera. So let me introduce our first speaker. Is Yen-Ting from Institute of Astronomy and Astrophysics, Academia Sinica in Taiwan. He earned his PhD in astronomy at University of Illinois at Urbana-Champaign in 2005 under the advice of Joseph Moore. Prior, he earned his bachelor at the National Taiwan University in 1999. His main research interest is observational cosmology, galaxy clusters, and galaxy formation evolution. And today he's going to talk us about statistical nature and mass assembly of brightest cluster galaxies. So please, the floor is yours. Thank you.
Thank you very much. Good afternoon. It's my great honor to be here. And I would like to thank Bill particular for his hospitality. Sorry, what's the...
I have to find the mic. Yeah. Sorry, might make it easier.
And allowing me to share with you some of our recent findings on the formation and evolution of brightest cluster galaxies.
The closest as possible.
Okay. Focusing on the statistical nature and the stellar mass assembly history. Here are my collaborators. So when the famous Schechter function first debuted in 1976, Schechter noticed that his nice function couldn't really describe the most massive, the so-called CD galaxies, which are giant elliptical galaxies with extended stellar envelopes like this. Using Sloan data by stacking 500 nearby clusters, I have shown that the luminosity distribution of BCGs appears to follow a log-normal form rather than the exponential drop as described by the Schechter function. So that hints on something special about the BCGs. So let's first examine how special BCGs are. Are they simply the extrema of the galaxy luminosity function, or are totally different population themselves? For this, we will use the Tremaine-Richstone Test. So basically, PR have devised two statistics that can be used to check whether BCGs represent the extrema of the distribution of the normal cluster galaxies. The two statistics are shown here, where delta is the magnitude gap between BCG and G2, the second most luminous galaxies, and sigma 1 and sigma delta represent the standard deviation of the BCG magnitude as well and the magnitude gap respectively. So T1 is defined to be sigma 1 over mean delta, and T2 sigma delta over mean of delta. So if BCGs are special, namely they form a distinct population, one can imagine that delta will be so big compared to the spread of the BCG magnitudes, and that will make both T1 and T2 small. Assuming a power law shape at the bright end of the luminosity function, TR showed that if BCGs are simply the extrema of the distribution, namely they are not special, then T1 and T2 should be greater than certain values, 1 and 0.82. For the clusters used for this study, we will use the sample from the Subaru Hyperster Prime Camp survey, HSC survey. So using the red sequence cluster finding algorithm, Chimera, we have 9,500 clusters at redshift between 0.1 and 1.4 over 1,000 square degrees with richness greater than 15, where richness is defined to be the number of galaxies more massive than 2 times 10 to the 14, so 10 to the 10 solar masses. So using 5,000 camera clusters at redshift between 0.3 and 1, here's what we found. For T1 as a function of redshift, we see that most of our BCGs lie below the TR limit of 1, so meaning that they are special. Whereas for T2, you see that the opposite trend happens. Most of our BCGs lie above the limit, meaning that they are not special. So what's going on here? Actually, when TR first applied their statistics to real data, they already noticed this inconsistency in the predicting power of these two statistics. And in this legal paper we just published, we argue that T1 is a better indicator for the specialness of BCGs, as it's less dependent on the properties of other cluster galaxies. So from now on, I will mainly focus on P1. And instead of using the limits derived by TR, which assume the power law shape at the right end of the luminosity function, to get a better handle of the statistical expectation, we instead tried using 1,000 Mach cluster ensembles. Basically, we just combine all galaxies from all clusters and make fake cluster ensembles from this. And this represents our statistical expectation. And for the real data, this is the measurement from our sample. And then we do 200 bootstraps, and that gives us a distribution. You can see that this is very far from the statistical expectation, both for T1 and T2. So we can safely say that BCGs are special out to redshift 1. And this holds true even if we split the clusters into high and low mass subsamples or high and low redshift subsamples. So we know BCGs are special out to redshift 1. Can we push the study to higher redshifts? Well, it's dangerous to do this with Chimera because beyond redshift 1, the incompleteness in the galaxy luminosity function is not accounted for. So it seems to me the best publicly available sample for this purpose is the KALA sample, which stands for clusters around radio log AGN. And the KALA team has made publicly available their HST Grisant data, which includes 128 redshifts in 15 clusters at redshift between 1.3 and 2. So again, using Mach ensembles, we get the statistical expectation, and the blue histogram is based on 5,000 bootstraps of the real data. So we see that the BCGs are special, but we know that recent data is kind of biased towards emission-like galaxies. So although the BCGs may well be self-forming in this redshift range from 1.3 to 2, it's still dangerous to use this kind of biased sample. So we decided to use this photometric catalog published by Simona May this year, and use the IRAC channel 1 selected galaxies to do the TR test. So with 116 probable members in 11 clusters from KALA, this is our result. So it's less significant. So we can say that BCGs are likely marginally special in this radio galaxy selected clusters. So how about theoretical expectations? By applying the TR test to 100 most massive halos from illustrious TNG 300 box, we found that the BCGs really stand out at redshift 2 and 3. So they are just special in this simulation. As for why, I think I have some ideas, but due to the time limit, I will skip this. but please ask me later if you are interested in. So, although I have utmost respect to the TNG team, I have many good friends in the team. I don't think there's any guarantee that the TNG model is correct beyond Redshift 2. So we need real data for this kind of study. So then, how do we get cluster samples beyond Redshift 2? Well, by combining Euclid and LSST, or later Roman plus LSST, we should be able to have a robust cluster sample beyond Redshift 2, either using PhotoZs or red sequence. And unfortunately, eROSITA will not deliver cluster samples out to Redshift 2. In the near future, CMB-S4 will have a cluster sample out to Redshift 3, so that's our best bet. I want to emphasize that spectroscopic data is critical. So we just know that DESI has a data release, and it gives us a taste of what can be done with a 4-meter telescope out to Redshift 1 or so. Next year, the super prime focus spectrograph survey will enable BCG evolution studies to Redshift 1.7. And MegaMapper or something like that, like MSE, will certainly extend the study to Redshift well beyond Redshift 2. So that's about the BCG specialness. Then I want to talk about the stellar mass assembly history of BCGs. Basically, I want to know, do we really understand how BCGs assemble their mass at redshift less than 1? Lambda CDM predicts quite a few mergers taking place at the very inner parts of massive halos like clusters. So for models like this, by DeLucia and Blazold, they predict substantial mass growth at later times. In this particular model, the BCGs typically acquire 50% of their final mass at redshift less than 0.5. To test theoretical predictions, we have devised several ways to study the BCG stellar mass growth history. For example, in this middle panel, we have constructed cluster samples in such a way that the low Z clusters can be regarded as the descendants of the high Z clusters in a statistical fashion. By that, I mean the properties of the low Z clusters should be similar to the descendants of the high Z clusters in our sample. So using this method, we see that the model prediction and data, which are shown as the red and blue points, agree fairly well between redshift 1.5 and 0.5 in terms of the BCG stellar mass. But below redshift 0.5, the two diverge. While the model BCG continue to grow, the observed BCG seem to stop growing. To further check this behavior, we then use a fixed number density selection of clusters to study BCG stellar mass at redshift 0.4 and 0.2 using data from Sloan. Here I show the stellar mass distribution at these two redshift ranges, epochs. And we hardly see any evolution of the distribution, while the theoretical model from Guo et al. 2013 predicts at least 30% evolution. Then we have the HSC data, so we can extend the study to redshift 1. So between redshift 0.3 and 1, we have 4 redshift bins, each occupying the same conmoving volume. And then in each of the bins, we select the richest 100 clusters and study the properties of the BCGs. And in this figure, I show the BCG mass on the y-axis and the cluster mass on the x-axis. The data points are color-coded according to their redshifts from high to low. And we see only about 35% growth between redshift 1 and 0.3. while the semi-analytic model predicts at least 80% growth. We recently developed a new method to address this issue, which is very general and can be applied to many cluster properties. What this method requires are, one, a numerical simulation that provides merger trees for halos, which is easy nowadays, and two, a measurement between the cluster mass and cluster observable. In HSC clusters, we use richness. So in Murata et al. 2019, they used wavelengthing to measure the richness mass relation or MN relation out to redshift 1. So with these two in hand, we can start from any halo along any merger tree. So we know the halo mass. Then using the high Z MN relation, we find a cluster whose richness is closest to the prediction from the MN relation. Then we can follow the merger tree down to lower redshift, here. And then we certainly know the halo mass. And again, using the MN relation at lower redshift, we pick a cluster whose richness is closest to the prediction from MN. And this way, we can connect two real clusters at two different redshifts. And this connection accounts for the scatter in the cluster mass observable relation, while at the same time incorporates the hierarchical buildup of structures. So by applying this method to the latest HSC camera sample, this is the result. Again, BCG mass on the y-axis and the cluster mass on the x-axis. And because of the way the cluster samples are built, you can consider this as a time axis as well. So I have three sets of data points representing three cluster samples. The red, green, and blue represent the most massive, intermediate, and lower mass clusters selected at redshift 0.3. So we can see how BCGs grow with time. So the point to the left are measurements at redshift 1.11, and the point on the right are measurement at redshift 0.62. So we see a fast growth at high redshift, and then the growth kind of slows down, which is in agreement with what we have found before. So the puzzle remains. While theoretical models predict a continuing growth of BCGs, our 4 different attempts have consistently shown that BCGs appear to stop growing at redshift less than 0.6, 0.5. So how do we reconcile this? It could well be that the halt in the stellar mass growth of BCGs may be due to the finite aperture used in observations. Nowadays, massive galaxies are believed to form in a two-phase fashion. In the first phase, a starburst creates a dense compact galaxy. And then in the second stage, the galaxy mainly grows in mass by accreting satellites at the outskirts. So here's an illustration. This is the surface density profile as a function of radius. So we see that the star formation happen in situ, mainly creates a compact galaxy, while the accretion mainly deposits mass at outskirts. So in this study done by someone whose name, unfortunately, I cannot pronounce, they use hydrodynamical simulations to study the BCG mass growth. So BCG mass as a function of time or redshift. So the red line represent the stellar mass formed in situ, while the blue shaded region is the mass when they consider BCG mass within a fixed aperture. So there appears to be reasonably good agreement with my measurement back in 2013. However, observing the BCG light out to large radii is very challenging. It requires very flattened image and also careful treatment of surrounding, the satellite galaxies in the cluster core. And only very few people in the world can do that well. And I'm not one of them. So I figured that perhaps observing the merger rates at the center of BCGs may be easier. So here I showed Sloan images of BCGs with multiple cores. These are examples of BCGs experiencing mergers with satellite galaxies. So because the core or the center of the satellites are dense, they remain visible while their outer parts are tidally disrupted. So we can certainly measure the merger rate, but that will require a time scale that has to come from simulations. And that makes the comparison with simulation kind of circular. So we decided to focus on the first term here, which we call the multiple core frequency, which is basically the number of BCGs with multiple cores divided by the number of BCGs in a complete sample. So using a volume limited sample of 73 BCGs from the Sloan 4 manga survey, which provides the stellar velocity maps, we can check whether the cores are physically associated with the BCGs or just chance projection and measure the multiple core fraction. This is how we proceed. So I show a BCG with a big core here. We first have to have a model of the BCG and subtract the main body of the BCG off. So this is our best model for the BCG, and this is the residual map. So you can see the core very clearly. Then in the stellar velocity map, we find regions with velocity deviating from the systemic velocity. And if this region spatially coincide with the residual map, then we identify that as a bona fide core. So this figure shows the velocity offset of the 30 cores that we have securely detected. And we regard cores with velocity offset within 500 km per second as candidates that will eventually lead to a merger. And we measure multiple core frequency of 0.11 plus minus 0.04. And then we make a comparison with the TNG 300. At redshift 0.1, there are 225 halos above our mass cut 10 to 14 solar masses. So we first have the idealized images of the BCGs, and then we added observational effects such as the sky noise and other observational things. And here you can see a small gallery of mock BCGs with multiple cores. And we do need to model the BCG main body and subtract the body off. And this way we measure a multiple core frequency of 0.08 plus minus 0.04, which is within 1 sigma from our measurement. So even the reasonably good agreement between the BCG in the BCG multiple core frequency between TNG and manga, we can use TNG BCGs to study the growth at the very inner parts. And we found that the growth rate is very small, only 1 to 4% per gigayear between redshift 0.6 and 0.1. So the lack of growth could indeed be explained by the finite aperture used in observations. And so maybe finally we have a good understanding of the BCG mass assembly. So I think my time is up, so I'll just very briefly summarize the talk. So we have shown that BCGs are special out to redshift 2. They are a distinct population. And are they born special? According to TNG, yes. Although I didn't have time to talk about that. You're welcome to ask me about this. But we really need real data to pin down how and why BCGs are born special. And then I have shown that stellar mass growth history from imaging survey seem to be in disagreement with theoretical models, but by measuring the multiple core frequency for a big sample of local BCGs, we think that we have a better understanding of how BCGs assemble their mass. So I'll stop here. Thank you very much.
Thank you so much. Do we have a question from the?
So I still cannot understand how you treat how you handle selection effects when you look for multiple cores, because the projection might play a very big role there. You know, like you take a coma cluster.
Yeah.
There's clearly emerging BCG. We don't know when it will merge, but it won't pass your test because you're looking at it from the side. So they are well separated in the sky, but they're two equally luminous galaxies that will sooner or later merge because they
Right.
together by 700 kilometers per second. On the other hand, you have a chance projection from the cluster. You will make all the same signature as you're looking for, so it will be like a separate core with distinct rate of velocities.
Right. So what I didn't mention is that we actually measure the core frequency within a very small aperture, 18 kiloparsecs. This is like the half-light radius of our BCGs. So in terms of coma, I mean, I agree with your point that this is kind of dependent on the viewing angle, but with our small aperture, I think this will not be an issue.
Okay.
Yeah.
Thank you. Could you go back to the plot you showed the cluster mass versus the BCG mass and you find that projectors is three different, yes.
Yeah.
And it looks like the BCG will stop growing in the inner part at the same ratio, or in other words, with the same BCG same mass, rather than the outer issue. So could you please give some comments on that?
Sorry, I actually don't get it. Can you say it again?
Yeah, because usually the x-axis is the Halo mass, right?
Right.
And the y-axis is the BCG mass.
Yes.
And things like that. And the final point of the galaxies you observe at the same ratio, or similar ratio, both blue, green, and red.
Yeah.
And but they have totally different Halo mass.
Right.
Quite similar BCG mass. So you info that this is kind of process that stop the growth of the mass of the BCG. So what's the physical mechanism?
So I should say that for these measurements, we use a so-called C model magnitude, which is kind of a match filter approach to measure the BCG photometry. So C model just choose whether a BCG is better described by an exponential profile or the divocular profile, and then choose the suitable weight to get the best measure of the BCG light. But it cannot go forever. So we kind of stop at like 50 kpc or so. So my point is, in theoretical models, the mass is mainly accreted at the outer parts. So if we only focus in the inner parts, we will not see much growth. But if we have the capability of measuring the light all the way to say 100 kpc, I believe this will continue to grow in better agreement with theoretical models.
I just wanted to mention that in terms of what's next, the South Pole Telescope 3G survey is been going for 3 years and it's going to go for another 2 years. We already have a few hundred clusters that redshift greater than 1. So
That's
that
good.
will become public long before
CMBS4.
CMBS4.
Right. I heard from Gil Holder that I think in a couple of years, SPT 3G will be as deep as CMBS4. So that's very, I mean, I certainly look forward to that.
Will be as deep, well, it's already as deep over small regions, and it will never, it will, SPT S4 CMBS4 over a large region will ultimately be 3 times deeper than the SPT survey.
Okay.
It's a matter of how many detectors there are.
Right.
SPT only has 10,000.
Only, yeah. Right. But I guess my point is we want to go beyond Redshift 2, and I'm not sure if SPT can deal
Yeah,
with it.
there's a couple, maybe not. For example.
Right. So we need I think at least 20 clusters so that TR tests can be meaningfully applied. Okay.
Thank you. Any more questions from people here? No questions from online, so let's thank Eileen again.
So let me
Okay.
stop sharing.
Let me
And
introduce
then-
our second speaker while he's setting up the.
Sorry, where is Zoom?
So,
Your slide is.
I'm happy to introduce
okay.
Dominika Krol. She's a 3rd year and probably last also year. No,
There are
fourth-
4 years
fourth
there.
year. So, one to last year PhD at the Jagiellonian University in Krakow, Poland, under the supervision of Lukas Stavars. Currently, she's a predoc SCFA. You might have met her in the Bachelor in
Thank you.
corridors in the last few months. And she's been working with Malgorzata on the broadband emission of young radio galaxies. Today, she's going to talk us about the broadband emission of compact X-ray obscure radio sources. Dominika, the floor is yours.
Thank you very much. Thank you for the introduction. So today I would like to talk about the project which I was working on during my stay in CFA. So broadband emission of a compact X-ray obscure radio sources. And let me start with a brief introduction about the X-ray emission of AGNs in general. So we observe hard X-ray emission from AGNs, and we believe its source is inverse Compton scattering of the soft photons in a hot plasma. And we associate the hot plasma with X-ray corona, and the soft photons are coming from the accretion disk. Then they are scattered in our corona. Part of the emission is just emitted as an X-ray continuum, and part of it is reflected in dusty torus, what adds the reflection features in the X-ray spectra, such as Compton reflection hump and fluorescence lines, from which the most prominent is an iron line. And our sources were chosen based on their features in the X-ray spectrum. So we are dealing with 3 sources, which are, all of them are heavily obscure in X-rays. And here you can see the X-ray spectrum of one of those sources. And here is the power law heavily absorbed component in the emission. Secondly, all of them have a detection of iron line at 6.4 kiloelectronvolts, and all of their in-strict luminosity in X-rays is between 10 to the power of 42 and 10 to the power of 44. They belong to a broader class of sources, which in radio astronomy are known as a compact symmetric objects. In general, compact symmetric objects have sizes below 1 kiloparsec, but our free sources are on the lower range of this, of the lower size range. They are between 7 and 25 parsecs. And therefore, they are likely to be still inside of the torus based on the recent measurements of the torus sizes in AGNs performed by ALMA. Our goal was to check if the scenario in which the inverse Compton scattering occurs within the radial lobes instead of commonly considered scenarios of X-ray corona as lamppost model or the base of the jet model is viable. So if we can explain the X-ray emission from our sources based on the inverse Compton scattering in the radial lobes. Namely, can we replace this general AGN image with an image in which the soft photons are scattered within the radial lobes? And since the radial lobes are still compact in our sources, we can expect that the emission from the radial lobes can be also reflected at the density torus, producing reflection lines. So in order to examine this, we were using the model of Stavage et al., which is dealing with the expanding radial lobes emission. So in this model, they take into account the dynamical evolution of the radial lobes. Also, it allows for various prescriptions of the electron energy spectrum injected at the hotspot. And then it calculates, we can calculate the energy evolution of those electrons, taking into account adiabatic losses and also radiative cooling components. Radiative cooling takes into account inverse Compton emission of the soft photon fields as infrared and UV, and also synchrotron emission. So in general, parameters of our model can be described. I will try to describe them using this picture. So first of all, we have an emission, radio emission of the radial lobes, which is produced by synchrotron radiation of the injected electrons. We describe them as the energy spectrum we described as a broken power law. It also depends on the jet kinetic power. Later, we also have the scattering, inverse Compton scattering of UV photons coming from the accretion disk and inverse Compton scattering of photons coming from the infrared. Since the line of sight, we see the objects through the torus, we do not observe directly UV emission, but we observe directly infrared emission. The emission also will depend within this model on the ISM density and the ratio of the energies of the electrons and magnetic field within the radial lobes. So in our modeling, we're using broadband data. Most of the data from radio to UV frequencies were coming from the literature. We're, however, using also X-ray photon indexes and fluxes, which were previously modeled and obtained based on Chandra, XMM, Newton, and NewStar data by our group, also in this work. We were using SMA data for sub-millimeter frequencies and gamma ray upper limits based on the Fermi-Lat observations. Those sources, all of those free sources, are not detected in gamma. However, those upper limits allow us to put some constraints on our model. So there are a lot of parameters in our model. However, some of them are directly observed. So first of all, we directly observe infrared emission from the galaxy. We also can measure linear size, radio turnover frequency, and the advanced velocity of radial lobes. Since we know absorption, X-ray absorption, we can calculate the ranges of ISM densities, assuming some characteristical scales on which absorption occurs, such as the linear size of our sources or the typical size of the Chandra extraction regions. So between 7 to 25 parsecs and some few kiloparsec scales. And overall, we were considering the ISM densities between 70 and 10 to the power of 4 per cubic centimeter. And our modeling was actually performed using the radio and high energy data. So using radio data, since we knew the radio emission, we could try to reproduce it with our model by changing low and high energy slopes of the electron energy spectrum, its minimum, maximum, and the break Lorentz factor, and also jet kinetic power. When it comes to high energy emission, it is mostly controlled by, first of all, ultraviolet emission, and also the ratio between the energy densities in the electrons and magnetic field, and also ISM density. So first of our result considers radio emission. So all three of our sources have very steep high frequency in a radio, high frequency drop in the emission. And it can be explained within the model only when we put the high energy electron spectrum and index in a very soft value. So we need to have a very soft high energy electron index in order to reproduce the observed radio emission in all of our three sources. And this kind of modeling was previously performed in the literature for a sample of other CSOs. And when it comes to our result regarding the high energy electron index S2, we saw that we need this kind of high value index only for the sources which are, first of all, have small linear sizes, and secondly, are exhibiting high absorption in X-rays. When it comes to high energy emission, our first result was that in general, X-ray emission is produced through inverse Compton scattering of infrared and ultraviolet photons within our model. So since we observe infrared emission directly, it gives us some kind of lower limit on the X-ray which can be produced in our model. So here you can see the example of one of our models for which the X-ray emission can be explained throughout almost only inverse Compton scattering of the infrared emission observed for the source. On the other hand, gamma ray emission is produced through the inverse Compton scattering of the ultraviolet photons, and therefore Fermi-Lat upper limits give us constraint on the ultraviolet emission. And here you can see the example of the source in which we are not able to get the emission, X-ray emission levels which are observed within our model. Because if we would increase the UV emission, which is not directly observed, so this is one of the parameters which we can change in our model, but we are not able to increase it further because that would overproduce the gamma emission. So we know that we require another X-ray component, which is not connected to the radio lobes. And in general, overall, the low ISM densities and the radio lobes, which are not in the equipartition, those parameters increase the X-ray emission within our model. So here you can see another example. This is actually the first source which I showed you before. And whereas for the equipartition model and the intermediate ISM density, from our model, we obtain X-ray levels which are comparable to the observed values. Then if we treat the equipartition and change it to and we change the ratio between energy densities and we lower the ISM density, then the expected emission produced by our model is much higher than the observed emission. So this quick summary of our result is that for one of our sources, J1511, we are able to explain the whole X-ray emission which is observed using only the model in which we produce X-rays as a inverse Compton scattering in radial lobes. On the other hand, in other source of our sample, J2021, which actually has also the highest X-ray luminosity, we need additional X-ray component. We are not able to explain the X-ray emission without violating gamma ray limits within this model. And the interesting case is OQ208, because depending on the ratio of the energy densities between magnetic field and the electrons, it can be either explained by our model or we need an additional component. Also, the ISM density plays a role in it. So as a conclusion, I can tell that at least two our sources, their X-ray emission can be explained using the model in which we have inverse Compton scattering on the electrons within the radial lobes. And since both of those sources have small linear sizes, which are smaller than measured torus sizes, we can expect that it may be a possible alternative to literature X-ray coronas. So to sum up all of the results which are presented, first of all, we have those two sources in which we can explain the X-ray emission within our model scenario as an emission in the radial lobes. We have also one source, which is also X-ray brightest of all of three, which requires additional component of around 10 to the power of 43 ergs per second. This additional component can be interpreted as due to, for instance, hot inner flow or X-ray jet, in general, any other X-ray corona scenario. Our data prefer densities which are around from 100 to 2000 per centimeter square, per cubic centimeter. And we estimated the jet power of in our models to be between 10 to the power of 42 and 10 to the power of 44. Moreover, when it comes to radio component of the emission, in all of the three sources, we need to have a very steep slope of the high energy electron distributions in order to reproduce the radio emission which we observe, which also is consistent with the lack of Fermi-Lat detection. Thank you very much.
Okay, do we have any questions from the in-person people?
Very nice. Just anecdotally, I heard that from the new polarimetry measurements, looks like the corona is not a point on top of the disk. It has to be extended, take a good fraction of the area. Is that consistent with this approach?
I mean, for sure, this one would be considering much higher volume of our X-ray emission, but it's difficult for me to say if it would be consistent with the results since I haven't seen it.
More questions? More questions? Yeah. Oh.
Thanks, this is nice. I was wondering if you have any relation to the age of this sources, measure kinematic age versus size versus the result.
So the age is below 400 years in those three sources. So they are very young. So as I mentioned, they are very compact, like even for the compact radio sources, they are below 25 parsecs. So together with the kinematic measurements, they are approximated to be younger than around 400 years.
Okay, so I've been told there is a question online. I cannot see. Oops. So
I can just speak up if I have the floor.
yes,
I was wondering what these sources would look like if you're viewing them more in line with the radial lobes. Would they be just ordinary sources, or would you be able to distinguish them in some way? And are there any examples of those?
I feel like in general, when it comes to young radio sources, we mostly are talking about them when they are on the plane of the skull, because then we can easily measure the distances. And since we have also measurements of the expansion, we can estimate the years, the age. And I believe it would be very difficult to do it if we were look from it from up. So honestly, it's I think it's difficult for me to answer to this question.
Okay, but there must be such sources, of course. So
Yes, of course.
So
but
your
of
answer
course.
is that they would be undistinguished then?
Yes, I believe it would be very difficult to distinguish them in the way in which we distinguish those class of sources.
Okay, thank you.
Okay, any more questions from here? I cannot see online. No, okay, so let's thank Dominika again.
Okay.
Thank you.